Welcome back to The Deep Dive, the show where we cut through the noise to get you truly well-informed. You know, every day we interact with AI in ways we barely notice. Maybe it's that song recommendation that just pops up and is perfect.
Right.
Or how your search engine it just gets what you meant, even if your search terms were a little vague.
Happens all the time.
And for many of you listening, especially if you follow AI, you've probably heard terms like vector space or semantic search thrown around. But what's the invisible magic actually powering all that? Often it's not even named.
Yeah, it works behind the scenes.
Exactly. So today we're diving into a really core piece of that puzzle, one that's often unseen. Embedding. Okay, so let's try and unpack this embedding. It sounds technical, maybe, but it's like this fundamental tech behind so many AI applications we use all the time.
It really is foundational. Search engines, recommendation systems.
Yeah, those AI chatbots that seem so smart.
Definitely those two.
So at its heart, embedding is basically turning data, like any kind of data, text, images, sound.
Pretty much anything, yep. Text, images, audio. It gets transformed.
Into what? Like coordinates that the AI can actually understand.
Exactly. Think of it as translating complex stuff into just a string of numbers.
A string of numbers, okay.
And once it's in that numerical form, the AI can do something really powerful. It can compare distances and find similarities.
Ah, okay. So it's like giving the AI a kind of sophisticated ruler.
That's a good way to put it.
To measure meaning.
Precisely. It's measuring the conceptual distance, the meaning. And what's so fascinating, I think, is how something that sounds quite abstract, turning everything into numbers, actually unlocks such huge practical power.
Right.
This deep dive, I hope, will really show the why it matters behind those numbers and how embedding lets AI have things that, we once thought were way beyond what machines could handle.
Okay, so let's get right to that core concept then. When we talk about embedding, what is it really? Like, how does it actually work to make these meaningful numbers?
Well, at its simplest, embedding is, it's a process. It transforms data into vectors.
Vectors. Okay, that sounds a bit mathy.
It can be, but think of it simply. A vector is basically just a coordinate point, like an address.
An address.
Yeah, but not on a flat 2D map. Imagine a huge city with hundreds, maybe thousands of dimensions, all interconnected. It's a point in that space.
Wow, okay. A multi-dimensional city.
Kind of, yeah. And the crucial part, the real insight, is that this number representation, this vector, lets the AI measure similarity. Let me give you a really concrete example. Think about the words cat and dog.
Okay.
When an embedding model looks at them, their vectors, their numerical forms, end up being very close together in that multidimensional space.
Why? Because they're similar.
Exactly. The model understands they share characteristics, right? They're both animals, often pets, furry, 4 legs, that kind of stuff.
Got it.
Now, contrast cat with, say, car.
Very different.
Totally different. So their vectors will be really far apart in that space. One's a living thing, a pet, the other's a machine. Fundamentally different natures.
Okay, that makes sense. The distance reflects the difference in meaning or concept.
Precisely.
So the model isn't just counting letters, it's actually getting the concept. But you mentioned text. Does this work for other things too, like pictures or music? Does that distance of meaning idea apply there?
Oh, absolutely. The principle is really general. It works just as well for images, songs, videos, pretty much any data you can think of.
Oh.
Well, take music. Imagine 2 love songs. When you convert them into vectors, their distance in the space will be pretty small.
Okay.
But compare a love song to, I don't know, a really heavy metal track.
Right. Very different vibe.
Very different. Their vectors will be much further apart. The AI picks up on similarities in musical elements, themes, even the emotional tone. And it represents all that as these numerical coordinates.
So that's how services can group songs or recommend new music that feels similar, even if the genre tags aren't quite right.
Exactly. It's looking at those subtle connections captured in the numbers.
Okay, I'm following, but I suspect this multi-dimensional space idea might still feel a bit floaty for some listeners. Is there a way to make it more intuitive, like more tangible?
Yeah, we can definitely try it. Let's use an analogy, maybe a travel map.
A travel map, okay.
Imagine the entire vector space, this multi-dimensional thing, as a giant, super detailed map. Like world scale.
Got it.
And every single piece of data, we're talking about a word, an image, a song, it has its own specific, unique location on this map. Now, on this map, things that are similar, they're like adjacent cities. They're really close together. Think about Paris and Rome, maybe.
Wow.
Geographically close in Europe, sure, but they also share deep history, Roman culture, similar architecture styles in places.
Okay, culturally close too.
Right. So their locations on our conceptual map would be near each other. But then you take Paris and, I don't know, New York?
Very far apart, different continents, different feel.
Exactly. Like places across half the globe on our map, separated by an ocean, totally different cultural backgrounds. Their map locations would be distant. And the key insight here, this is really the magic, the profound part of embedding. It's not just comparing if words are identical. That's what old keyword search did.
Right.
Instead, embedding is about comparing how close their meaning is, their essence.
Ah, okay. Meaning not just matching letters.
Precisely. This ability to grasp semantic relationships, the intent behind the data, that's its true charm. That's what makes it so revolutionary for how AI understands information.
That travel map analogy really helps visualize it. Fantastic. I mean, I know I've definitely fought with search engines where my keywords weren't exactly right,
We've all been there.
or gotten recommendations that just felt totally off base. So if this is the secret sauce for understanding meaning, where are we actually seeing embedding making a difference, like right now in our daily life?
Oh, it's everywhere. You're bumping into it constantly, probably without even realizing it. A huge area is semantic search optimization.
Semantic search, meaning-based search.
Exactly. It goes way beyond just matching the exact words you typed. It finds content based on the meaning or intent behind your query.
Okay, give me an example.
All right, say you search for running shoe recommendations. A traditional search might only find pages with those exact words.
Yeah, that sounds familiar.
But with embedding, the AI understands that suitable jogging sports shoes means basically the same thing, so it can pull up those results too, even if the wording is different.
Wow. Okay, that's much smarter.
It's a huge shift. We're moving from just matching text strings to the AI actually understanding what you're trying to find. Think about how much better that makes things like customer support searches or finding information in huge databases.
Yeah, absolutely. What else?
Well, recommendation systems, definitely. This is where embedding really shines in personalization.
Like my music streaming service.
Exactly like that. It analyzes the embeddings, the vector coordinates of the songs you listen to. Then it finds other songs or artists whose vectors are close by on that conceptual map we talked about. Similar genres, styles, moods. Even if you haven't explicitly tagged them, it gets the underlying connections.
So it's mapping my taste numerically.
In a way, yes. Or think about shopping online. You buy coffee beans.
Yep.
And suddenly it recommends a coffee grinder. That's not just because people buy them together, though that helps. It's also because the system understands the semantic link that these things go together conceptually.
So my streaming service isn't just eavesdropping. It's actually mapping my musical soul onto a giant number grid.
Yeah.
It's kind of amazing and maybe a tiny bit creepy.
Huh. Well, it's definitely impressive tech.
And what about those chatbots? The really smart ones we talk to now that seem to understand complex questions? Is embedding part of that too?
Absolutely. Especially in Q&A chatbots that work off a specific knowledge base, like a company's internal documents or FAQs.
How does it work there?
Well, all that information, all those documents and articles, they get converted into embeddings first, stored as vectors. So when you ask a question, even if you phrase it differently than the original text, the AI can find the most relevant vector in its database, the piece of information that's semantically closest to your query, and use that to give you an answer.
So that's how they seem to understand rather than just find keywords?
Exactly. And beyond chatbots, it's crucial for things like document classification and clustering, automatically grouping similar articles, sorting huge piles of documents based on what they're about, not just keywords, saves massive amounts of manual effort.
It's really incredible how versatile this one core idea is. Now, for listeners who are maybe getting curious about the tech itself, or maybe even thinking about playing around with this, what are the key technical bits and pieces under the hood? What terms should they know?
Sure. If you want to dig a bit deeper, there are a few main concepts. First, you need the tools that actually create the vectors. These are called embedding models.
Okay, the vector generators.
Right. They're specialized AI models trained on absolutely massive amounts of text and data to learn the relationships between words and concepts. Popular examples you might hear about are OpenAI's models, like text embedding 3 large.
I've seen that one mentioned.
Yeah, it's very capable. And others like SentenceBERT, which is really good for understanding the meaning of whole sentences.
So these models like OpenAI's or SentenceBERT, are there reasons to pick one over the other? Like, what are they best at?
That's a good question. Generally, something like OpenAI's text embedding 3 large is known for being Well, really robust and versatile. It works well across many different types of text and tasks, and it's easy to use through their API.
Okay, so good for general purpose stuff.
Right. SentenceBERT, on the other hand, is often highlighted for tasks specifically involving semantic similarity, like finding sentences that mean almost the same thing. Plus, you can sometimes run models like SentenceBERT locally, which gives you more control, maybe for privacy or specific fine-tuning. So it kind of depends on your exact goal and setup.
Gotcha. So you have the models creating the vectors. What then? Where do these numbers live?
Good point. You need a place to store them efficiently and, crucially, search through them quickly. That's where vector databases come in.
Specialized databases just for these vectors.
Exactly. Think of them as highly optimized storage systems designed specifically for these multidimensional number coordinates. Examples people use are Pinecone, Weaviate, maybe FAI, which is more of a library.
And they're fast at searching.
Super fast.
Oh.
They're built to find the nearest neighbors, the vectors closest to your query vector, very, very quickly. That's essential for real-time things like search results or recommendations.
Makes sense. Okay, models create vectors, databases store and search them. How do they actually measure the closeness or similarity?
Right. The measurement itself, there are different ways, but the most common method by far is called cosine similarity.
Cosine similarity, okay.
Yeah. Without getting lost in the geometry, it essentially measures the angle between two vectors in that multidimensional space.
The angle?
Yep. The smaller the angle between two vectors, the more similar their direction, and thus the more similar their meaning is considered to be. A 0-degree angle means they point the exact same way, maximum similarity. A 90-degree angle means they're unrelated. It's a really neat mathematical way to capture that conceptual closeness.
Angle equals meaning similarity. Fascinating. Okay, that gives a good picture of the tech stack. Hearing about all this, I bet listeners are thinking about real-world cases. You mentioned search. Have you personally worked on a project where switching to embedding really made a difference, maybe fixed a problem with an older system?
Oh, definitely. I worked with a company a while back on their internal document search. Classic problem.
What was happening?
They had this huge library of internal documents, procedures, HR policies, you name it. But employees just couldn't find anything using the old keyword search. It was incredibly frustrating for them.
Give me an example.
Sure. Someone might search for, say, holiday overtime regulations. Makes sense, right?
Yeah, totally clear what they mean.
But the actual official HR document used the term holiday work subsidy.
Yeah.
Because the keywords didn't match exactly.
0 results.
Exactly. 0 results. So people wasted time searching, gave up, called HR. Huge inefficiency, lots of annoyance.
But what did you do? Let me guess.
Yeah.
Embedding.
You guessed it. We implemented an embedding-based system. We took all their documents, converted them into vectors. Then, when an employee searched, the system didn't just look for keyword matches. It converted their search query into a vector too, and then looked for the document vectors that were semantically closest in meaning in that multidimensional space.
And did it work? What was the result?
The difference was night and day. Seriously. The search hit rate, the number of times people actually found what they were looking for, went way up. Far fewer 0 result searches.
I bet employee satisfaction improved too.
Massively. People could finally access the company's knowledge base effectively. It made a real tangible difference to their daily work.
That's a great success story. Any pitfalls, though? Any lessons learned the hard way?
Oh yeah, there's always a lesson. The biggest one, and it sounds basic, but it's crucial, is data cleaning.
Ah, the quality of the input data.
Exactly. You can have the most sophisticated, state-of-the-art embedding model in the world, but if the documents you're feeding it are messy, full of errors, outdated, or just plain irrelevant,
Garbage in, garbage out.
still applies. The model can only represent the meaning of the data it's given, so ensuring your source material is clean, well-organized, and actually relevant before you embed it is absolutely critical. Don't skip that step.
That's such a valuable, practical point. Even with amazing AI, the groundwork matters. So for our listeners who are maybe feeling inspired now, thinking, okay, I want to understand this better, or even maybe I could try implementing this.
Yeah.
What's your advice for a beginner starting out with embedding?
My #1 piece of advice for beginners is start with existing APIs. Don't feel you need to build or train an embedding model yourself right away. That's a whole other level.
Use the tools that are already out there.
Exactly. Services like the OpenAI Embeddings API or others from providers like Cohere or Google,
Yeah.
they make it super easy. You literally just send them your text.
And they send back the vector. the numbers.
Yep, they send back the string of numbers. It lowers the barrier to entry massively. You can focus on using the embedding, seeing what they can do, rather than getting bogged down in the model training part initially.
Okay, that sounds manageable. What's a good first exercise someone could try?
A great way to get a feel for it is to take a few short pieces of text. Maybe grab like 3 news articles about the same topic, and then maybe 2 more articles about something completely different.
Okay.
Use an API to get the vectors for each of those 5 articles. Then try doing a simple similarity search, maybe using cosine similarity. Many libraries make this easy. See how the vectors for the 3 related articles are numerically close to each other.
Small angles between them.
Right, and how they're far away from the vectors of the unrelated articles. It makes the concept really click when you see it with your own data.
That sounds like a really practical way to build intuition. Good idea. Anywhere else people should look as they learn more?
Definitely. As you get more comfortable, it's really useful to understand the connection between embedding and something called RAG.
RAG. What's that stand for?
Retrieval Augmented Generation.
Retrieval Augmented Generation.
Yeah.
Okay. How does that relate?
Well, RAG is a really powerful technique used with large language models, the LLMs like GPT-4 that power things like ChatGPT. What RAG does is it first uses embedding to retrieve relevant information from a specific knowledge base, like finding the closest document vectors we talked about earlier.
Okay, so step 1 is find relevant stuff using embeddings.
Right. Then step 2 is it takes that retrieved information and feeds it to the LLM along with the user's original question.
So it gives the LLM extra context.
Exactly. It augments the LLM's generation process with specific relevant facts. Think of it like giving the LLM an open book exam. Here's the relevant chapter. Now answer the question based on this.
So it makes the LLM's answers more accurate and grounded in specific information, less likely to just make stuff up.
Precisely. It significantly reduces hallucinations and makes the LLM's responses much more factual and reliable, especially when dealing with specific domains or recent information the base model might not know. So understanding embedding is really key to understanding how RAG works, and RAG is becoming super important.
Wow. Okay, so embedding isn't just for search and recommendations. It's also a key enabler for making these powerful LLMs even better. This has been incredibly illuminating. We can really see now how embedding acts as this sophisticated coordinate system for AI.
That's a great way to frame it.
It's what lets AI go beyond surface-level words and actually grasp the distance of meaning between different bits of information.
Yep, the semantic distance.
And it's working away silently behind the scenes in so much of our digital life, isn't it? That Spotify playlist, the Google search results that just work.
It's quietly making everything much smarter and more intuitive. And this kind of understanding raises an interesting point, I think.
What's that?
By demystifying these core principles, like embedding, you start to realize that a lot of this seemingly super high-tech AI, it's not actually magic. It's built on understandable concepts.
Right.
Which means that building cool AI applications, or even just understanding them deeply, isn't limited to some elite group.
Right.
It's becoming accessible to anyone willing to learn these foundations. It shifts things from feeling like impenetrable tech to, well, understandable methodology.
That's a really powerful thought. The more we grasp these building blocks, the more we can all participate, innovate, and just use AI more effectively. It democratizes it in a way.
I think so.
Well, thank you so much for this fantastic deep dive today. Really appreciate you breaking down embedding for us, and thank you all for joining us. Next time, we're going to tackle something a bit different, more on the human side of learning this stuff, overcoming self-doubt while learning AI. Should be really interesting. Remember to subscribe to this channel so you don't miss that discussion. We'll see you then.